all kind of familiar with thin wall pressure vessels. If I draw something simple like this, I think you'll recognize it immediately. Imagine like a propane tank, a tank that holds a compressed gas. We see those around all over the place. We assume that these have constant cross sections and hemispherical ends. But there are other thin-walled pressure vessels we see around us a lot. Think of a can that holds a carbonated drink, like a Coke can. Here's another, maybe less common example that I've got. This is a little container that's been cut open, but this had an end on it with a little rounded cap. And this originally held pressurized carbon dioxide, CO2 bottle. And they use these for all kinds of things. In the U.S., they use these for shooting BB guns and larger versions of something like that to shoot paintball guns. Those are thin-walled pressure vessels. A thin wall there's no hard definition, but a thin wall is one where the wall thickness is small compared to the diameter of the cylinder as a whole. If the cylinder diameter is 20 times the wall thickness, that's a pretty good rule of thumb. So thin wall pressure vessels have large diameter compared to the wall. Now the wall could be thick if the diameter is big enough. I saw a submarine in a museum one time, and they had the side of it cut open. This is up in a museum in Chicago, Museum of Science and Industry. There's an old World War II submarine, but they've cut the side of the hull open so you can get in. You don't have to get in through the hatchways anymore. When you walk through there, you can actually see the pressure vessel, and it's surprisingly thin. It's, I don't know, 10, 15 millimeters thick, something like that. And the diameter of the submarine as a whole is several meters. So that's a very thin-walled pressure vessel. A thick-walled pressure vessel is one where the wall thickness is large compared to the diameter, or not small perhaps. Think of like a hydraulic cylinder or a cannon barrel. If you're ever in a museum and you see like a tank, well, the tank barrel may have a bore, that hole down the middle, maybe 100, 120 millimeters. The walls are thick compared to that. The walls, at least back by the breech, may be as big as the bore. Definitely not a thin wall pressure vessel. So we're sticking with thin wall pressure vessels because the expressions are relatively simple and because these are by far the most common in a lot of fields. Okay, there are two kinds of stresses we're worried about here. They're both normal stress, but they arise from slightly different phenomenon. The first one is longitudinal stress. Okay, stress that makes the pressure vessel want to get longer. Pressurized inside, so it's going to want to try to blow up like a balloon, but the walls are not elastic like a balloon is. They're resisting the pressure much more effectively than a balloon would. So this doesn't change shape very much. Now, longitudinal stress is what makes it want to grow, makes it want to get longer. All right? There's another kind of stress. It's called hoop stress. Hoop stress is what makes the diameter want to get bigger. And that's easy to imagine. There's pressure inside the pressure vessel, and the diameter is going to try to get bigger. So this is, we'll call that sigma L for longitudinal stress, and we'll call this sigma H for hoop stress. Now I'm not sure I would have called it hoop stress, but nobody asked me. If you're looking for a way to think about it, think of the old-fashioned wooden barrels that have those metal hoops around them. Those hoops are what hold the barrel staves together. And although I don't know that the barrels were necessarily pressurized, those hoops are a good reminder of what hoop stress is. Now, these have related but slightly different expressions for them. The expression for longitudinal stress is pressure times the mean diameter over 4t, and the expression for hoop stress is pressure times the mean diameter over 2t. All right? Now, this is really important. That number in the denominator makes a big, big difference. Because that number is smaller than that number by a factor of 2. That means hoop stress is bigger than longitudinal stress by a factor of 2. All right? Now, we're assuming a lot of things here. We're assuming constant cross-section. We're assuming constant uniform wall thickness. And we're also assuming here hemispherical end caps. Even if you don't have hemispherical end caps, sometimes you're close enough. Now, what this means is that when a pressure vessel fails, it tends to unzip. It tends to blow the side open. It doesn't tend to blow the end caps off. because this stress is twice that. Now, there are some examples of pressure vessels designed to have the end caps blow off. I'm thinking primarily of glass bottles. Go talk to somebody who brews their own beer. If you put too much sugar in it and it fizzes up too much and the pressure inside the bottle gets too high, many bottles, not all I imagine, but many are designed so that when they do fail, they blow the bottoms off them rather than blow the sides out and send broken glass everywhere. That blowing the bottom off the bottle is a much safer failure mode than sending glass flying everywhere. Right? Go talk to a brewer, they'll tell you. So what I want to do now is spend a few minutes telling you where these expressions come from, and in the following video we'll do some calculations. All right? Let's erase this here. And let's cut imagine the pressure vessel cut open here. So we're looking at it in cross section. That's a terrible drawing, but that'll do. Now, I'm drawing this as a thick wall so you can see what's going on. This doesn't apply to thick walls. That's slightly better. Okay. Any kind of stress, in this case longitudinal stress, is going to be a force divided by an area. Well, the force comes from the pressure inside the pressure vessel times the area that the force acts over. Okay? So that's going to be pressure times the area, we'll call that XC for cross-section, cross-sectional area of the entire tank. That area is the area of the wall here. That's the area that can resist the force. All right? So that's going to be the circumference times the thickness. And let's do that times thickness. Okay, and I'm going to clean this up in a second here. Well, cross-sectional area is going to be pi over 4 times the diameter squared, or pi r squared if you prefer. But the area is pi over 4 times some diameter squared. Well, we have an inside and an outside diameter. What we're going to work with is something called mean diameter. It's halfway between the inside and the outside diameter. Okay? And the mean diameter is the outside diameter minus 1 wall thickness, not 2. The interior diameter, that diameter right there, is the outer diameter minus 2 wall thicknesses. Okay, but that's not what we're doing here, so don't make that mistake. We're using that diameter. So here we have P times that area now is going to be pi over 4 times the mean diameter squared. Circumference is pi times the mean diameter times the thickness. All right? So there we go, and a very little bit of algebra will make this work out for us. So that crosses out, that pi crosses out, and I get P dm over 4t. Okay? So that's pretty straightforward. The next thing we're going to worry about is hoop stress. And we use the same kind of logic, but now we're cutting the pressure vessel open from the side. Excuse me. And the way we're going to do that is look at this thing from the side, where that's the area of the metal that can resist the pressure and the force, and the pressure acts over an area that looks like this. Now we can pick any length we want, and the stresses are not dependent on the length of the pressure vessel, so we'll call that 1. So hoop stress is F over A. Okay, that's 1 times the mean diameter times the pressure. And area now is thickness times 1 times 2, because there's 2 thicknesses we've cut now. 2 times 1 times the thickness. Well, those 1s drop out. And what you're going to get, you can see this coming. Okay, so there you go. Now we know where both of our expressions come from. The next thing we're going to do in the following video is make some calculations using these 2 expressions.